Hello, and welcome to AMAT362, Probability for Statistics at UAlbany. This is lecture 4, and I want to start off with hopefully something you recognize. Stare at this triangle of numbers I've got here, where I have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on. Do you recognize where this comes from? Hopefully you do, because this is the famous Pascal's triangle. How's this pattern generated? So for example, if I've given you these several rows of numbers, which collectively form a triangle, how might you add the next row? Ideally, you recognize that the rule is that I start with creating another one, and then I add the two numbers above it to get the next number in the row. So this would give 6 and 15 would give 21. Let's check that that works. Notice that if I take 1 and 2, this adds to give 3. And if I add 1 and 3, this adds to get 4. And I add 3 and 3 to get 6. And 3 and 1 to get 4. And just continuing this pattern allows me to produce a new row. So let's go ahead and fill it out. So 1, 7, 21, 35, 35 again, 21, 7, 1. Where does this appear? It's not just a curiosity, but shows up in all over mathematics. In particular, if I look at the expansion of x plus y to the nth, the binomial formula tells me that the coefficients for the kth term in this expansion is n choose k, where I have x to the n minus k times y to the k, where I sum over k equals 0 to n. So let's check that that works, and let's identify the corresponding rows. I want to think of this as corresponding to the 0th power, and this being the coefficients of x plus y raised to the 1, this being x plus y squared, and this being x plus y cubed. First of all, let's check that that x plus y squared works out. Hopefully you all remember FOIL. X plus y times x plus y equals x squared plus x times y plus y times x plus y squared, which when I collect these terms gives me x squared plus 2xy plus y squared. So these numbers are actually reading off the coefficients in this expansion of x plus y to the n. This is useful for the following reason. Remember, we considered the question of how many subsets of an n element set are there? Think for just a few seconds, hopefully you remember that the answer is 2 to the n. Now, let me show you where this number comes up and how it's connected to the choose formula that we introduced last lecture. So obviously 2 to the n is the same thing as 1 plus 1 to the n. And so if I look at how this formula works, I can have, thinking of 1, this first one is x, and the second one is y. I should have 1 to the n plus n times 1 to the n minus 1 times 1 plus n choose 2 times 1 to the n minus 2 times 1 to the 2 continuing on through n choose k, where I have 1 to the n minus k and 1 to the k. Of course, all of these are just equal to 1. And I can think of these coefficients over here as being n choose 0. This sort of corresponds to choosing the empty subset. And finally, this last term over here being n choose n, which is equal to 1. That's where I choose all my elements to be in my set. So recall that n choose k, which written out is n factorial over n minus k factorial times k factorial, is the number of k-sized subsets of an n element set. There's also a remarkable duality principle at work here. Which is that choosing a subset is equivalent to choosing its complement. Remember, those are the elements not in my set. So what that says is that if I look at n choose k, that's the same thing as choosing its n minus k size complement. So n choose n minus k. And that just comes from switching the roles of these two numbers. Check that for yourself to make sure you believe me. All right, let's move on and see how this shows up in probability. We're going to talk about this in more detail, but the choose formula is absolutely fundamental in what's called the binomial distribution. I'm going to show you first the prototypical example of where the binomial distribution shows up. So here's the question. Suppose I flip the coin 6 times. I'm going to think of this as a fair coin. So that means that the probability of heads or tails is equal. What's the probability of getting exactly 2 heads out of 6 flips? So again, the first thing you need to do is figure out what is the sample space in this problem. So what is the sample space? So this is the space of possible outcomes, which we can think of as sequences of flips, F1, F2, F3, F4, F5, F6, where each Fi is either a heads or a tails. So the size of omega is the number of options for each flip. That's 2 times 2 times 2 times 2 times 2 times 2, which is 2 to the 6th, which is 64. Now, how do we choose, how do we calculate the size of A, which is the event where exactly 2 heads occur? A equals the event where exactly 2 of the Fi are heads. So what that amounts to is choosing 2 of the positions in my 6 to be heads. So how do I calculate the size of A? Well, this has to be I have 6 possible flip numbers to choose to be my heads, and I need to choose 2 of them to be the ones that are heads. Let's go ahead and work out and see what that is. So that's 6 factorial over 4 factorial times 2 factorial, which is 6 times 5 divided by 2, which is 30 divided by 2, which is 15. So that tells us that the probability of A is equal to the size of A divided by the size of omega, which is 15 over 64, which works out to roughly a 23.4% chance. Now notice, you may have been led to believe that one way of approaching this problem is like, well, first I have to choose which of these locations I want for my first heads. And so you said, well, I've got 6 possibilities. And then once I've chosen that location, I can choose the second one, in which there are 5 possibilities. That would have led you to believe that 6 times 5 is the number of ways. But there, what you're doing is you're keeping track of what was my first heads and what was my second heads. We don't care. All we care about is that there were 2 heads somewhere in our sequence of 6 flips. So we have to make sure we instead use this choose notation, especially when we're only concerned with an unordered sample of 2 heads out of 6 flips. So let's look at some other situations where these kinds of counting problems emerge. Oops. Here, we're going to look at another example. So here's another Scrabble problem. Oops. Which addresses a bigger question. So let me save this. Which is a much important, bigger question, which is permutations with repeating letters. And it all comes down to, let's say, this other question, which might look a little different from what we've been considering, but I'm actually show you is another way of thinking about this choose notation. And it's also going to allow us to think about a wider range of problems. So here's the ultimate question. So how many ways can I rearrange the letters in toot? So what I mean by that is, can we recognize when I switch these O's? Personally, I can. And in fact, you shouldn't be able to tell the difference, which gets exactly at that question of when I was trying to count the number of ways in which I would get 2 heads out of my 6 flips. I said, well, you could think of it as, let me take 6 possible locations for my first heads. And then of the 5 remaining head locations, I choose one of those. So you'd say that's 6 times 5, there are 30 possibilities. But since I don't care which one is my first heads and my second heads, I could have reversed those roles. So let's say if my second heads, the second flip was my heads, and then my third one was my second heads, then I could have also considered the possibility where I chose my second flip to be my second heads and my third one to be my first heads. That's why we had to divide by 2. But this word problem is going to show us another more general method here. So let's see. Let's go ahead and write them all out. So here's the answer for how many ways can we rearrange toot? Well, obviously there's T-O-O-T. And then I could do T-O-T-O, that's Toto. And then I could do T-T-O-O. Or I could do O-O-T-T. Or I could do ot-ot. Or finally, I could do Otto. So that's 6 possibilities. Now, what's the general formula here? Well, the formula goes something like this. Here's the general answer. So if I have a word with n letters, let me say a word of length n with L distinct letters, which appear in sub 1, in sub 2, all the way up through in sub L. So you want to think of this as the number of times the second distinct letter appears. Where, of course, since this has to account for the length, so a number of times, in particular, n1 plus n2 all the way up through n sub L equals my length, n, then the number of rearrangements is given by the wonderful formula n factorial over n1 factorial times n2 factorial on down through n sub L factorial, which we sometimes write as n multi-choose n sub 1, n sub 2, n sub 3, all the way down through n sub L. And we call this the multinomial coefficient. Because this tells you something about the coefficients of x1 plus x2 on through xl raised to the nth power. So let's go ahead and apply this formula in some examples. Let's do some more examples. So just to keep that up there right now for a second, if we see we've got Another classic example is first auto. So let's go ahead and show that this works. So here n is equal to 4. Our first letter is going to be, I don't know, the number of O's, which is 2, and the number of T's, which is equal to 2. Then this formula says that there are 4 factorial over 2 factorial times 2 factorial, which is 4 times 3, it's 12, divided by 2, which is 6, which you already verified above by writing out all of the examples. But we don't have to do that in general. Let's do it again with a different word. Example. So apple. How many ways are there of rearranging the letters in the word apple? Distinct ways, meaning ways in which you can tell them apart. So here we need to count the number of A's, P's, L's, and E's. So we've got a number of A's is equal to 1. Number of P's is equal to 2. The number of L's is equal to 1. The number of E's is equal to 1. So we end up getting, once we sum all these numbers up, 5 factorial divided by 1 factorial times 2 factorial times 1 factorial times 1 factorial, which is same thing as 5 times 4 times 3, which is 60. It's a good thing we didn't try to write those all out, because that would have been a long effort for something we can do a lot more quickly with math. Let's do my personal favorite example. How many ways can we rearrange the letters in falafel? I do love falafel. Take a moment to see if you can approach this, this problem yourself. So again, what we need to do is first count the number of times each distinct letter appears. So first we need number of F's, which is 2. Number of A's, which is 2. Number of L's, which is 2. The number of E's, which is 1. And I think that accounts for all of the letters. There are just 4 distinct letters, F, A, L, and E in falafel. Now what's the length of falafel? Well, it's 7. And that agrees if I sum up all these numbers here. So I get the number of ways is 7 factorial divided by 2 factorial times 2 factorial times 2 factorial. And I could put 1 factorial, but 1 factorial is the same thing as 1. So it's fine if we don't write it there in the denominator. All right, so that's the general method. Now you might ask yourself, why does this work? And where else can we use this formula? So let's first address this, this question of why does this work? And then we can also get at some other ways of expressing that number and some applications. So here's the big question. So why does this formula work? So let's again imagine that you superimpose some extra structure so that you can actually tell these letters apart. And then we're going to divide out by things we know we can't tell the difference from. So step 1 is, let's make every letter distinct. So imagine I look at auto. Then I could say, well, I've got a little O, but now with like a 1 sitting below it. And I've got a T with a 1 sitting below it. Then I've got a T with a 2 sitting below it. and another O with a 2 sitting below it. Don't worry, we're not doing chemistry here. Now, when I do this, because I can now distinguish every letter, I would say that the number of rearrangements I can distinguish is, in this case, 4 factorial. In general, we would say it's n factorial, which is the length of the word. Here I'm assuming I'm making every letter distinct by maybe adding just little marks next to it. Now, I need to recognize that this number of permutations is overcounting certain permutations. In particular, in reality, I can't tell when I switch these two t's. The only reason I can tell is because I added a little 1 and a 2 next to each of them. So step 2 is very simple. It just says, so divide by the permutations of divide by the number of permutations that you can't really tell apart. So in this case, T1 and T2, in this formula up here where I use 4 factorial, I can't really tell when I switch these two t's, so T1 and T2, assuming I drop those little subscripts. I can't actually recognize those as different. So that means that's a 2 factorial extra permutations. In similar spirit, when I take O1 and O2, then I reverse those, O2 and O1. These I also need to recognize are the same. So that's another 2 factorial extra perms. And since I can do each of these permutations on these letters separately, I then multiply, because there are 2 steps, permuting the O's and permuting the T's, that I need to reconcile. So that means that my number now goes n factorial, of course, divide by the number of letters of each type, n sub L, which in this case works out to be 4 factorial, our total length factorial, divided by the number of permutations I can't really tell apart, which in this case actually ends up being 4 choose 2, because there are only 2 types of letters. Now you might ask, is that a coincidence? Turns out it's not. So let's see why. So let's go back to the coin flipping problem. So to better describe how I can think of the number of ways in which I can get 2 heads, so and again, this is, I should interpret this as exactly 2 heads, corresponds to the number of rearrangements of H, H, T, 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 T. So you can think of this as being the result of flipping my coin twice, getting 2 heads right off the bat, and then getting 4 tails. So using the formula we just derived back on this page, this one right here, I can now think of this event as being counted by the number of possible rearrangements of the word hut, which we just learned is, well, first I count the total length, which is 6 factorial. I look at the number of t's, so it's going to be n factorial over n, the number of h's factorial times the number of t's factorial, which ends up being 2 factorial times 4 factorial, which again is 6 times 5 divided by 2, which is 15. So you can think of this as also a formula for choosing where your locations are in my list of 6 possibilities. So in this case, the connection between the number of ways of rewriting this nonsense word, HHTTTT, ends up coinciding exactly with the number of ways of choosing 2 positions unordered from 6 possible locations, those being the 6 possible flips. Let's go ahead and see another example where this formula comes up. So another way in which this shows up, so other applications. So here's other applications. Of our multinomial formula is assigning in people to L groups, with each group getting n sub 1, n sub 2, on down through n sub L people. So here's the typical kind of question where you might be asked to use this formula in this way. So how many ways can I assign $2,000 students to 3 schools where school 1, the number of students in school 1, so number of students in school 1, which you could think of maybe as the capacity of that school, is 1,000. The number of students in school 2 is 500. And the number of students in school 3 is also 500. So first, think about how you might approach this problem if you hadn't learned anything in today's lecture. Take a second just to think. Well, here's one way in which you might approach it is, well, I've got 2,000 students. I want to choose 1,000 of them to go to school 1. How many ways are there of doing that? Well, there's 2,000 choose 1,000 this is a number of ways of choosing 1,000 students from 2,000. And you're just saying, all right, you're all my school 1 students. Once I've picked from this set of 2,000 students. Now, once you've done that, you've got 1,000 students left. And so you pick 500 of them to go to school 2. Choose 500. And so that's the number of ways of choosing 500 from the remaining 1,000. And so what do you have left? You have another 500 students left. It's 500, choose 500. And just like in kickball, whoever's last, there's no choice. So this also just equals 1. Now what happens when we write out this expression? Let's just take a look. So remember, you first take our 2,000 factorial, and you take 2,000 minus 1,000, which in this case is 1,000 factorial. And then what's left is 1,000 factorial. This is my n minus k. I think this is my n minus k factorial, and this is my k factorial. Then I have 1,000 choose 500. So again, that's in this case 1,000 factorial over 500 factorial, 500 factorial, and then times 500 factorial over 500 minus 500 is 0 factorial. And then what's left is 500 factorial. So again, here you have to remember, so I'm going to do this in green. So nota bene means note well that 0 factorial is always equal 1. And that shows up just down here. All right, but anyhow, let's go ahead and sort of cancel away, see what we're left with. Well, what do we get? So we have 1,000 factorial here, canceling with 1,000 factorial here. Of course, we've got 500 factorial here, 500 factorial here. And what's left, surprisingly, is 2,000 factorial, 1,000 factorial, 500 factorial, 500 factorial. So what is happening here? Notice this is exactly the formula for 2,000, choose 1,000, then 500, then 500. This is our multinomial formula. It's also counting the number of ways of rewriting a word of length 2,000, where there are 1,000 repeated letters of type, let's say A, and there's 500 repeated B's, and there's 500 repeated C's. Now, what does this have to do with anything? Well, if you wanted to solve this assignment problem, here's one way you could do it. You could line up. So imagine you line up your students, and you've got student 1, student 2, student 3, all the way up through student 2,000. And so what we're going to do is just put down 1,000 A's. So imagine you've got an A. And maybe let me just go ahead and write out a few more characters so this is a little clearer. So here I've got student 4, got student 1,500, got student 1,501, I've got student 1998, student 1999, student 2000, And so once I've lined up all my students, I want to figure out, how do I assign them to schools? Well, here's an algorithm for doing it. Well, let me just create a random permutation of a word which has 1,000 A's. Let me call these, let me do this red. And let's say I've got a couple A's here, an A here, maybe an A here. And then imagine I've got 500 B's. Maybe I've got a B here, a B here, a B here. And let's say I've got also 500 C's. So I've got 500 C's. I've got 500 B's, and I've got 1,000 A's. And so here's the procedure for assigning students to schools. I create a random permutation of this 2,000 length word, which has 1,000 A's, 500 B's, 500 C's. And now that I've got this word lined up, the assignment process just says like, okay, well, student 1 got an A in this permutation, so they're going to go to school A. And student 2 got a B in this permutation, so they're going to go to school B. And student 2,000 got a C, so they're going to school C or school 3. So our algorithm looks something like this is goes to school 1, and this goes to school 2, and this goes to school 3. And so now the number of ways of assigning students to schools, I can think of as just in terms of lining them all up. They're all distinct, so that's fine. I'll just go by birthday and time or what have you. I then generate this big permutation of which there are, as we know, 2,000 factorial divided by 1,000 factorial and 500 factorial, and then 500 factorial possible permutations. And each permutation gives me a unique way of assigning students to schools. All right, let's finish this because we're nearly done with one more application that's maybe more pertinent to poker. Again, one of the pioneering purposes of probability and combinatorics was to essentially help people make money, especially by being smarter when it comes to gambling and calculating odds. So let's look at another example in that vein. So let's look at a poker example. So how many ways are there of dealing six people 5 card hands? So again, let's go that same way. How would you do this problem intuitively, assuming you didn't know anything from today's lecture? So let's try to do that. Let's this is our question. Here's our first answer. A sub 1. Well, you might reckon that, well, if I just need to choose from my 52 card deck 5 cards to give to player 1. And then I've got 47 cards remaining to give to player 2. And then I've got 42 remaining cards to give to pick 5 from, and then 37 remaining cards to pick 5 from there, and then 32 pick that 5. All right, we're up to 5 people. We need to do our 6th person. It's 27 remaining, so 27 choose 5. Again, I think of this as a number of ways of choosing 5 cards for player 1, and all the way down. But another way of thinking about this, so this is so here's another way. This gives us our sort of answer 2 is, well, I need to assign my cards so that of my 52, I have 5 going to person 1, 5 going to person 2, 5 going to person 3, and so on. Now notice that doesn't say what happens to the remaining cards. So I'm going to imagine that there's a 6th or 7th person who gets the remaining 22 cards. That's just going to be cards that are left over so that we can deal from. So let's just use our formula. So in this case, what we get is something like 52 factorial divided by 5 factorial player 1 cards, 5 factorial player 2 cards, 5 factorial player 3 cards, 5 factorial player 4 cards, 5 factorial player 5 cards, 5 factorial player 6 cards. Now notice these numbers only add up to 30, which isn't equal to 52. And if you go back briefly to our formula right here, I needed that the sum of the numbers in the denominator be what's up top. So n1 plus n2 plus n3 plus nl needs to equal n. And right now that's not true here. So this goes where we imagine we've got our 7th person here. That's just the discard pile. So there's nothing deep about that. But again, you can imagine what I'm going to do is I've got my deck of cards. And I just like going through this for the cartoon, for visualizing here, is I've got, card 1, card 2, card 3, card 4, card 21, card 22, card 35, card 36, all the way up through card 51, card 52. And what I'm going to do is imagine that player 1 gets any card with the label A, and player 2 gets card with label B, and so on and so forth. And so I can now sort of repeat exactly the same construction I did before, where I've got let's say A's over here, and then I've got B's over here. And then say I've got C's over here, and I've got D's over here, and I've got E's over here, and then F, which you can barely see. These are going to be our discards. So those are our 22. So we've got I'm going to say 22 F's. Again, really hard to see, but I've got 5 A's, 5 B's, I've got 5 C's, I've got 5 D's, And so, my gosh, I messed up here slightly. I wasn't able to count my letters. I've got 5 E's. So that gets us 5 players cards. I've got 5 E's. And let me magically erase one of these. Oops. Let's imagine I've got a bunch of G's. G's for a misspelled junk. Those are our discards. This is our discard. And so shuffling is just equivalent to, basically coming up with one of these random permutations and then picking that card from the deck. Magically, we wouldn't even need to necessarily move the deck, but I could have a computer generate one of these sequences, and it would tell me that, okay, player 1 is going to get the first, fourth card, and player 2 is going to get the second card. Player 3 is going to get the third card. Player 4 is going to get this 22nd card. Player 5 is going to get the 36th card. Player 6 is going to get the third card. And I think I said something that should have been player 5, but anyway, we get our discards as the ones with the orange color. So this is a sort of important combinatorial trick that I want people to have the flexibility for thinking. It's going to allow you to model a lot of different problems. All right, so that's it for today. I look forward to seeing you in class soon.